TAC units, also known as packaged terminal air conditioners, serve the purpose of providing localized heating and cooling to individual rooms or spaces within a building. Their operation typically involves cycling on and off at frequent intervals as they strive to maintain the desired temperature setting. Because of this operational characteristic, TAC units are generally not categorized as continuous loads. However, an exception to this categorization arises when TAC units are employed in scenarios that demand sustained operation, such as maintaining a consistent temperature in environments like server rooms or other critical spaces. In such cases, their operation might be regarded as continuous. According to the National Electrical Code, specifically Section 215.2a on feeders and branch circuits dedicated to serving continuous loads must be sized to accommodate not less than 125% of the load's full demand. Conversely, in situations where the load is not deemed continuous, the feeder and branch circuit conductors can be sized to handle 100% of the load. In the context of designing an installation for TAC units, it's crucial to assess whether they will operate in a continuous mode. If it is reasonably assumed that the TAC units will operate in a non-continuous mode, the conductors can be sized to accommodate 100% of the load. For instance, considering a scenario involving 15 TAC units with a 19.6 amps maximum circuit ampacity, or MACA, each connected to a three-phase panel, the load on each leg, assuming balanced distribution, would be 196 amps. Under the assumption of non-continuous operation, a 225 amps feeder and overcurrent protection device, or OCT, could be selected for the panel. The MACA, a critical parameter for TAC units, represents the maximum current the unit is designed to draw under normal operating conditions. It's specified on the unit's nameplate and is determined based on comprehensive testing and adherence to industry standards. The MCA value incorporates factors such as the unit's compressor, fan motor, and any auxiliary component. When sizing conductors and overcurrent protection devices for TAC units, the MCA serves as the foundational value for ensuring the electrical system can safely and reliably handle the unit's power demands. Notably, it is generally not necessary to apply an additional continuous factor to the MCA rating, as it already accounts for the unit's operational characteristics and potential for sustained operation. In general, a continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. Factors that determine whether a load is continuous or not include how the equipment is used, the type of occupancy, and whether or not the load will be operating at its maximum current draw for extended periods. When dealing with electrical loads, particularly those with the potential for continuous operation, it is imperative to exercise caution and meticulousness in load calculations and conductor sizing. Overestimation, while seemingly conservative, can lead to inefficiencies and unnecessary expenses. Conversely, underestimation poses significant safety risks, potentially resulting in overheating, insulation degradation, and even electrical fires. Therefore, electrical engineers and designers must adopt a balanced approach, carefully considering all relevant factors and applicable codes and standards to ensure both safety and efficiency in electrical installations. When sizing electrical conductors for continuous loads, the National Electrical Code, or NEC, mandates that the conductors be rated to handle at least 125% of the continuous load current. This provision is in place to account for the sustained heat generated by continuous operation and to prevent overheating and premature failure of the conductors. To accurately determine the appropriate conductor size, the continuous load current must be multiplied by 1.25, and the resulting value should be used to select a conductor with an ampacity rating equal to or greater than this calculated value. In scenarios involving multiple continuous loads supplied by a single feeder or branch circuit, the 125% factor is applied to the sum of all continuous loads. Additionally, any non-continuous loads connected to the same circuit must be added to the total to determine the overall load demand. For instance, consider a scenario where a feeder supplies 2 continuous loads of 20 amps each and a non-continuous load of 10 amps. The continuous load current would be 20 amps plus 20 amps, totaling 40 amps. Multiplying this by 1.25 yields 50 amps. Adding the non-continuous load of 10 amps results in a total load demand of 60 amps. Therefore, the feeder conductors must be sized to handle at least 60 amps. In addition to conductor sizing, overcurrent protection devices, such as circuit breakers and fuses, must also be carefully selected to protect against overloads and short circuits. The overcurrent protection device should be rated to trip at or below the conductor's ampacity to prevent damage to the conductors and connected equipment. For continuous loads, the NEC imposes additional requirements on the overcurrent protection device rating. Specifically, the overcurrent protection device must be rated at not less than 125% of the continuous load current. This requirement ensures that the overcurrent protection device will not trip prematurely due to the sustained heat generated by continuous operation. To determine the appropriate overcurrent protection device rating, the continuous load current is multiplied by 1.25, and the resulting value is used to select an overcurrent protection device with a trip rating equal to or greater than this calculated value. In cases where the calculated value does not correspond to a standard overcurrent protection device rating, the next higher standard rating may be used, provided that it does not exceed the conductor's ampacity. For instance, consider a continuous load of 40 amps. Multiplying this by 1.25 yields 50 amps. If a 50 amps overcurrent protection device is not available, a 60 amps overcurrent protection device may be used, provided that the conductor's ampacity is equal to or greater than 60 amps. In addition to adhering to the NEC requirements for conductor sizing and overcurrent protection, it is crucial to consider other factors that may influence the overall performance and safety of the electrical system. These factors include ambient temperature, conductor rating, voltage drop, and equipment ratings. Ambient temperature can significantly affect the ampacity of conductors. As the ambient temperature increases, the conductor's ability to dissipate heat decreases, resulting in a reduction in its ampacity. The NEC provides rating factors to compensate for the effects of ambient temperature on conductor ampacity. These rating factors are applied to the conductor's base ampacity rating to determine the adjusted ampacity rating for the specific ambient temperature conditions. Conductor rating is also necessary when multiple conductors are bundled together in a raceway or cable. The close proximity of the conductors restricts their ability to dissipate heat, leading to a reduction in their ampacity. The NEC provides rating factors to account for the effects of conductor bundling on ampacity. These rating factors are applied to the conductor's base ampacity rating to determine the adjusted ampacity rating for the specific number of conductors in a bundle. Voltage drop is another critical factor to consider when sizing conductors. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can impair the performance of equipment and reduce its lifespan. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, conductors should be sized large enough to handle the load current without excessive voltage loss. Equipment ratings must also be carefully considered when selecting conductors and overcurrent protection devices. All electrical equipment is designed to operate within specific voltage and current limits. Exceeding these limits can damage the equipment and create a safety hazard. The NEC requires that all electrical equipment be labeled with its voltage and current ratings. Conductors and overcurrent protection devices must be selected with ampacity ratings that are equal to or greater than the equipment's rated current. In addition to the general requirements for conductor sizing and overcurrent protection, the NEC provides specific requirements for certain types of loads and equipment. For example, the NEC provides specific requirements for motor circuits, air conditioning equipment, and electric heating equipment. These specific requirements are designed to ensure the safety and reliability of these types of loads and equipment. When designing electrical systems, it is essential to consult the latest edition of the NEC and to follow all applicable codes and standards. The NEC is a comprehensive set of rules and regulations that are designed to protect people and property from electrical hazards. Failure to comply with the NEC can result in serious consequences, including fines, lawsuits, and even criminal charges. In conclusion, sizing conductors and overcurrent protection devices for continuous loads requires careful consideration of several factors, including the continuous load current, ambient temperature, conductor rating, voltage drop, and equipment ratings. By following the NEC requirements and considering these factors, electrical engineers and designers can ensure the safety and reliability of electrical systems. When dealing with a scenario involving TAC units in an existing building, a practical approach would involve assessing the operational characteristics of these units. Firstly, determining whether the TAC units will be operating in a continuous mode is paramount. If they are expected to cycle on and off frequently to maintain a desired temperature, they may not be considered continuous loads under the NEC definition. Secondly, if the TAC units are deemed non-continuous, the conductors can be sized to handle 100% of the load. This can lead to a more efficient design, potentially allowing for the use of a smaller feeder and overcurrent protection device. Thirdly, consulting with the manufacturer of the TAC units can provide valuable insights into their expected operating conditions. The manufacturer may have data or recommendations regarding the typical duty cycle of the units, which can help in determining whether they should be considered continuous loads. Fourthly, engaging with the end user of the TAC units, such as the hotel management, can provide additional information about how the units will be used. They may have specific requirements or expectations regarding temperature control, which can influence the operational characteristics of the units. Fifthly, if the TAC units are intended to maintain a constant temperature in a critical environment, such as a server room, they should be considered continuous loads. In this case, the conductors and overcurrent protection devices must be sized to accommodate 125% of the continuous load current. Sixthly, even if the TAC units are not expected to operate continuously, it is prudent to consider the possibility of future changes in usage. For example, the hotel may decide to use the TAC units to maintain a constant temperature in a storage area. In this case, it would be prudent to size the conductors and overcurrent protection devices to accommodate the potential for continuous operation. Seventhly, the MCA specified for the TAC unit is based on the unit's nameplate rating and already incorporates factors such as the compressor, fan motor, and auxiliary components. It is generally not necessary to apply an additional continuous factor to this rating. Eighthly, when selecting conductors and overcurrent protection devices, it is important to consider the ambient temperature and conductor rating factors. The NEC provides tables and guidelines for adjusting conductor ampacity based on ambient temperature and the number of conductors in a raceway or cable. Ninthly, voltage drop should also be considered when sizing conductors. Excessive voltage drop can impair the performance of the TAC units and reduce their lifespan. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Tenthly, carefully review all relevant sections of the NEC, including 215.2a on, to ensure compliance with all applicable codes and standards. Consulting with a qualified electrical engineer can provide additional guidance and ensure that the electrical system is designed safely and efficiently. In summary, when designing an electrical system for TAC units, it is essential to carefully assess the operational characteristics of the units, consult with the manufacturer and end user, consider the potential for future changes in usage, and adhere to all applicable codes and standards. By following these steps, electrical engineers and designers can ensure the safety and reliability of the electrical system while optimizing its efficiency.